Before we learn Taylor series, which is a power series, we should first learn about a general power series. So a power series is written as the sum from n equals 0 to infinity of c sub n times x to the n. Here the c sub n's are constants and x is the variable. So if we write this out, we have the constant term c naught plus c1x plus c2x squared, etc. The first question I want to answer is, when does this power series converge? We can make use of the ratio test for convergence. So this converges if we look at the series far away. So it converges if the limit as n goes to infinity of the ratio of two consecutive terms. So here would be c sub n plus 1, x to the n plus 1, divided by c sub n, x to the n. And we consider the absolute value of this is less than 1. So when this condition holds for values of x, then this power series will converge. So we can solve this for x. This is x sub n plus 1 over x to the n, the absolute value. So this says that when the absolute value of x then is less than, and then we still have a limit here. So the limit as n goes to infinity, and we bring cn over cn plus 1 to the other side. So it would be c sub n over c sub n plus 1. So when the absolute value of x is less than the limit of the ratio of these coefficients, then the power series converges. This thing here has a name. This is called the radius of convergence. So that the absolute value of x is less than the radius of convergence, then the power series converges. The use of the term radius comes from complex functions, and we won't be covering that in this class, but it's an interesting topic in higher mathematics. Okay, when a power series converges, according to this ratio test, we say that the power series is absolutely convergent. What that means is that even if you take the absolute value of each term in the power series, it will still be convergent. A nice feature of an absolutely convergent series is that if you differentiate the power series, you can differentiate it term by term. And if you integrate the power series, you can integrate it term by term. It's very easy to differentiate term by term. So if we look at the derivative of this series, the sum from n equals 0 to infinity of c sub n x to the n, if I just look at the right-hand side here, the derivative of the constant is 0. The derivative of c1x is just c1. The derivative of c2x squared is just 2c2x. And the derivative of c3x cubed would be 3c3x squared, etc. Okay? So easy to differentiate term by term. If we wanted to integrate, so let's do the indefinite integral. So the sum from n equals 0 to infinity of c sub n x to the n, we're going to integrate dx. Then if we integrate the right-hand side term by term, first we get rid of the constant because this constant here will be c naught x. But remember that the indefinite integral is always plus a constant. So we can introduce the constant in the front here. Let's just call it c. And then we're integrating c naught, so that becomes c naught x. And then we're integrating c1x, that becomes c1x squared over 2, and then so on. Okay, so every term gets integrated. Okay, So that's the kind of the general theory of power series. We'll be needing this. Let's just look at an example now. So let's look at one example. Let's look at the following power series. So we have the sum from n equals 0 to infinity of x to the n over n factorial. This will turn out to be a very important power series. What is the radius of convergence here? So we can look at the radius of convergence. Right, so the radius of convergence is the limit as n goes to infinity, c sub n over c sub n plus 1. So it's the limit as n goes to infinity of c sub n over c sub n plus 1. So c sub n is 1 over n factorial. And c sub n plus 1 is 1 over n plus 1 factorial. We don't need the absolute value sign because all of these coefficients are positive. This simplifies. So this is the limit as n goes to infinity. So this has an n plus 1 factorial over an n factorial, right? And that n plus 1 factorial divided by n factorial is just n plus 1. So that's equal to the limit as n goes to infinity of n plus 1. And as n goes to infinity, that goes to infinity. So the radius of convergence is infinite. That means that this power series converges for all values of x. That's why it's such an important power series. We can differentiate that. We can integrate that. Let's see what happens if we differentiate it. If we take the derivative of this power series, n equals 0 to infinity, x to the n over n factorial. That would be the derivative term by term. So we can bring the derivative inside. So that would be the sum of n times x to the n minus 1 over n factorial. What is the index here? So the 0 term goes to 0. So what we have left is 1 to infinity. We can cancel one of the n's. So that becomes the sum of x to the n minus 1 over n minus 1 factorial. And that's from n equals 1 to infinity. And then finally, at n equals 1, this is just x0 over 0 factorial. So we can shift this index down and shift these exponents and the coefficient up 1. So this becomes a sum from n equals 0 to infinity of x to the n over n factorial. Right? So these are identical if we just, instead of starting at 1, we start at 0, and then we lift these up. N minus 1 becomes n minus 1 factorial becomes n factorial. But this is kind of an amazing result. This says that the derivative of this power series is equal to the same power series. Okay, the derivative of a function given by this power series is equal to the function. We'll see that this is the exponential function. Okay, let me summarize. Here I want to give a general formula for a power series. We applied the ratio test for convergence to this power series, and we find that this power series converges as long as the absolute value of x is less than the limit as n goes to infinity of the absolute value of the Cn coefficient divided by the Cn plus 1 coefficient. We call this ratio the radius of convergence. When a power series, when the values of x are less than the radius of convergence, If we differentiate the power series, we can do it term by term. If we integrate the power series, we can also do it term by term. I'm Jeff Chasnov. Thanks for watching, and I'll see you in the next video.